Hello everyone. In this video, I'm really glad to share something about this machine learning project on predicting the cirrhosis using some medical data. And in this video, I will basically cover three parts. First, I will explain some key steps of the modeling and pre-processing. And then I will explain a little bit how we choose the models and why certain models are especially suitable for this data set. And also, I want to share some insights from the results and their implications for the real-world applications. So let's begin with the key steps of the pre-processing. Apart from the regular steps like dealing with missing values, here I want to focus first on the encoding target because it's really important for this data set. So the dataset originally classified disease stages from 1 to 4. To simplify our task, we converted this into a binary classification problem where stage 4, representing late stage cirrhosis, was labeled as 1, and all other stages were labeled as 0. So this binary transformation can help us to focus on the modeling on identifying critical cases of advanced diseases. And then we want to deal with the skewness because many numerical features like bilirubin levels and collateral level had some long-tailed distributions, so there's some skewness. So to address this, we applied a logarithmic transformation, use the log1p tool here. So this transformation can reduce the impact of some extreme values and can bring the feature distributions closer to normal, which can help us to train the model better, especially for some models like logistic regression. And also, speaking of some extreme levels, we want to deal with the outliers too. So, there are some extremely high bilirubin levels can distort the model's understanding of the data. So we try to use some methods like turkey rule outliers to ensure that we kept these values while ensuring no important information was lost. And also for categorical variables such as gender and presence, we use this domain encoding to transfer them into numerical representations. It's better for the model training. And after that, we also do some standardization of the numerical features while we are doing the modeling, including bilirubin and age and cholesterols and so on, to use the standard scalar. So this ensured that all features had a mean of 0 and a standard variation of 1. So this standardization process can prevent features with larger ranges, such as age. So it will be better for our model performance. And also we want to address the imbalance of this model. So like where late stage cirrhosis cases were significantly fewer, we use SMOTE to generate synthetic samples for the minority cases, which can improve the model's recall and its ability to detect some late stage cases. And finally, we want to validate our model, so we use the 5-fold cross-validation. This process can split data into 5 subsets, rotating one as a validation set while the other were used for training. And this ensured that our models were evaluated on some unseen data multiple times, which can provide us with a more reliable model. So after completing all the pre-processing, we come to the modeling step. So using PyCaret, we automated the compression of several models, including logistic regression, random forest, extra trees. So this tool can help us to quickly evaluate all the models and their performance based on some metrics like accuracy, F1 score, recall, and then select the best models for us. So for this project, to look at the experimental setup and the step here, we evaluate multiple models like I mentioned, And then let's start with maybe the logistic one. So we can see here. So the logistic regression, after all the pre-processing and modeling, it achieved the accuracy of 33.65, and the F1 score is 62.9%. So it performed consistently across the data set, and it has low variance, making it ideal for simpler data patterns. But thinking it from the bias and variance trade-off perspective, so it may have higher bias, meaning that it may not be very suitable for very complex data set like this, because it may struggle with capturing more complex relationships like what happened in this data set. So next, we can see like random forest model. It is a tree-based model, and it's robust to the outliers and can handle mixed data types like this very effectively. So it achieved an accuracy of 75.75%, and its F1 score reached to 63.18%. So by averaging predictions across multiple decision trees, it can reduce the variance and capture complex patterns in this data. But still, based on the variance and bias trade-off, its slightly higher variance may exist, and it means it may be more sensitive to the training data. And also, we can see the extra tree classifier. It seems that it provides the best result. So similar to random forest, it can use some random splits to improve computational efficiency while retain high accuracy. So we can see it achieved the highest accuracy of 75.77% and a very balanced F1 score. So it also provides some important rankings, help us to identify some numerical levels like bilirubin, albumin, and ascites as key predators of this disease. So like we can see, PyCaret played a very key role here to help us to compare all the metrics among different models very quickly. It provided a very efficient way for us to choose among models. And also based on the results of this project, we can see some important insights like features may be really important for this disease include bilirubin levels, albumin levels, and the presence of ascites. They were especially important to predict the cirrhosis progression. And these findings may align with existing medical knowledge, which can prove that these models are basically reliable. And when it comes to the model performance, we can see like tree-based models like extra trees or random forest, they can demonstrate high accuracy and a really balanced F1 score. So they're very suitable for like broader screening applications. But if we focus on like minimizing false predictions, that means in this case, like we want to ensure no critical late-stage cases were missing, maybe a model like linear discriminant analysis may be more appropriate. So we can see in real-world applications, we need to consider comprehensive factors to choose models. And the choice of model depends on specific context and purpose. Like for this case, for the healthcare screening industry, so recall is maybe often prioritized because we want to avoid missing severe cases. So, but also we want to, reduce the risk of the clinical supports like extra trees may offer a really good balance of the accuracy, interpretability, and also efficiency. So maybe in the future, expanding the data set like this with more samples can improve the model performance, and we can incorporate additional clinic features to make the accuracy better, and these steps can help us to choose and train better models in the future for the healthcare screening industry. And that's all of my sharing. Thanks for listening.